In part 2 of this series, I'll show you how to use Euler's method to numerically solve differential equations, as opposed to in part 1 where we graphically solved them. The question reads, find the approximate solution to y prime is equal to x squared over y with the boundary condition that y is equal to 2 when x is equal to 3. Calculate y for x equaling to 3 to 10 in steps of 1. The first thing that I'll do is outline my first point, and they've given it to us. It's 3 and 2. That's our first point, and what I will do with this point is substitute it into my differential equation, which I'll highlight, and this will end up giving me the slope. So let's do that as step 1. And as I do this, I'll be creating a table of values. So I have y prime, which equals to my slope, is equal to 3 to the power of 2 over 2. That's like saying 9 over 2, and that equals to 4.5. So that is our slope. And as I mentioned, I'll create a table at the same time. So I have x and y, and my first point is 3 and 2. What I want to do next is find out my next y coordinate. So I have an x coordinate of 4, and I want to find out my next y coordinate. To do that, I'll take this 4.5, the slope, and multiply it to the steps that they asked us in the question. They said they wanted steps of 1. So I'll multiply this by delta x, and this will give me delta y. So let's go ahead and do that. 4.5 times 1, which was given in the question, gives us a delta y of 4.5. Now that I found my delta y, to find my next y coordinate, I'll take 4.5 and add it to 2. So here I have 4.5 plus 2 is equal to 6.5. That is my next y coordinate. Let's do one more. So at x is equal to 5, once again I'll substitute 4 and 6.5 into my differential equation. I'll do my work over here. I have y prime, which is equal to m, and that is equal to 4 as my x, which becomes 16, 4 to the power of 2 is 16, divided by 6.5. My slope, therefore, I'll use my calculator for this calculation, is equal to 16 over 6.5, and that gives me 2.46. m is equal to roughly 2.46. As before, I'll take my slope of 2.46 and multiply it to delta x, which is equal to 1. That's 2.46. Next, I'll add 2.46 to my previous y, which happened to be 6.5. So I'll add this, 2.46 plus 6.5, that gives me my next y value, which equals to 8.96. Now technically you're supposed to do this up until you get x is equal to 10. And if you've done it correctly, your completed table should look like this. So the completed table has been provided below, and you should end up with a table with two columns, namely this column and this column. Notice that it matches what we've been doing so far. We had 3 and 2, 4 and 6.5, 5 and 8.96, and you're supposed to go down all the way to 10. And you're probably wondering about the other two columns. Well, normally we use numerical methods for a differential equation whose exact solution cannot be found. Here we have used an equation whose solution is known so that we can check our answer, and that's the only reason why we've done this. And because we know the exact solution, we can actually come up with the exact y values. The solution is actually 3y squared is equal to 2x to the power of 3 minus 42. And this is how these values were found, by substituting x's into here and solving for y. And also notice that the difference between our approximate solution using Euler's method and the exact is not too much. Take a look at the error. For example, the error at 10, namely x is equal to 10, is only 0.6% off. Shown on the screen right now is a graphical representation of our approximate answer versus the exact y values. And there you have it. That is how to use Euler's method to numerically solve a differential equation.